So I would suggest that we can start now. Welcome to all of you to our today's Interreg Northwest Europe or OIP4NWE WebTalk on PICs for LiDAR systems. I think it's a very nice topic, but so this is our agenda for today. So we start with the welcome and then introduction of the project by Marija Trajkovic, and then we go into our main topic today, Coherent FMCW LiDAR systems by Davide Canavesi from SCANTINEL PHOTONICS GmbH. We have an open discussion, and after that, our colleague from Brussels, Jürgen van Erps, will introduce the Innovation Support Fund. So we have in our OIP4 NWE project, we have vouchers for companies who would like to test our pilot line, which is emerging. So, but first of all, I would like to give the floor to Marija.
Thank you, Hendrik. Let me first share my screen. Well, as Hendrik said, my name is Marija, and I come from Eindhoven University of Technology. I will briefly present the consortium of OIP4NWE who organized this webinar. We are a consortium of 11 partners with the coordinator in the Netherlands, TUE, and then partners spanning from Netherlands, Belgium, Germany, France, and Ireland. In total, 11 partners. And target are to increase the maturity and scaling of open access photonic integrated circuits in indium phosphide technology. Another thing we are working on is to provide technology support to SMEs who are looking to increase the maturity of their PIC-based products and to establish an open innovation environment for generic indium phosphide PIC technology. And it starts from the application need, design, fabrication, packaging to the final product. And where we are mainly focusing on in this consortium is on the fabrication aspect and the packaging aspect. So we have partners who are doing fabrication, we have partners who are doing packaging until we get the final product. With that said, that means that we are working between TRL 5 and TRL 7. So we want to increase, as mentioned, the maturity of these products. However, the main obstacles on the way are reliability, cost, yield, and scalability. Therefore, the main aspect of the process improvement is working on the epitaxy, yield, and stability. And we are also working on increasing the functionality of this generic platform by introducing new building blocks. So this would be the fabrication, manufacturing aspect of PICs. And then we also have the packaging of photonic integrated circuits, namely focusing on micro optics, optical fiber arrays, high-speed interposers, and thermal management. So these are all of the aspects which different partners in this project are working on. And together we are working with SMEs who are part of this project who are going to verify this platform. Later on, you will hear from our colleagues from Vrije Universiteit Brussels about the Innovation Support Fund, where we have a certain number of vouchers open to the SMEs who want to make advantage of this and experiment with this platform. So what is offered is the fabrication of photonic integrated circuits by Smart Photonics. Then we have the external optics design by VUB. And finally, we have packaging from Tyndall. But you will hear more about this in the final presentation. So that was a short introduction. If in any case you have questions, feel free to ask them, or you can also send an email to this email address.
Okay, thank you very much. I would suggest that maybe Davide can also already start his screen sharing while I'm introducing him. So today's topic are LiDAR systems. So as you know, modern vehicles are equipped with a wide range of sensor systems, such as LiDAR systems, to relieve the driver, for example, in terms of distance control or collision avoidance. But I think this topic is even getting more important because in future these systems will also enable autonomous driving for vehicles. And our guest today is working precisely on these systems. It's as already mentioned, Davide Canavesi. He's been business development manager at SCANTINEL PHOTONICS in Ulm for over a year. And the interesting thing about SCANTINEL is that it's a spin-off from the Carl Zeiss AG. So I think there's a huge impact behind this company, not with their own, not just with their own innovation, but also with the background they have. And therefore, I would like to give the screen to Davide Canavesi.
Thank you for this kind introduction. Can you see my screen, first
Yes.
of all? Yeah, and can
Perfect.
you hear me? Yeah, the
Yes.
two sticks,
Yeah.
sticks. In those days are the most important questions. Okay, so yes, this is what we are going to see in the next 20 minutes. I will introduce you to Scantinel, and then I will explain you FMCW LiDAR, which is the future technology in the LiDAR space, and how we are targeting a PIC-enabled solid-state FMCW LiDAR. Then I will also share some results that we have achieved throughout our development until now, and then we will close with a summary. So as a very starting point, on the left you see how the final system should look like, and here you see it looks like a standard camera, but you can think it about like an active camera. So the light is not just received by the optics, but is also emitted. So you have a light coming out from one laser, and then the light comes back and then is processed by the camera. So what we are working on, and the very core element of our technology, is the combination of silicon photonics together with advanced optics. And here you see in this picture the bluish or light blue chips. They are silicon photonic chips, and they are combined and packaged into a very compact solution that then interacts with a collimator optics. And in this way, we do achieve a solid state scanning, and then light and the ranging approach we are using is FMCW, and I will explain you later what it is. On the right side, you see what's the end goal of all these systems. You want to create a so-called point cloud where you can reconstruct the scene you have in front of the vehicle in 3D. And here you see the car, you see the trees. So from this information, then the perception system of the vehicle will decide how to drive the vehicle in a city or in this type of scenario. Now, a little bit of history about Scantinel. All the activities started back in 2016, and as said, it was within Carl Zeiss. Then all the FMCW activities ended up in a product for metrology, so close range but very high resolution, sub-micrometer resolution. But it was clear that the big market was the automotive, with all the autonomous mobility topics popping up. So the activities then focused into bringing the FMCW technology in the automotive space. And in 2019, the activities were moved under the umbrella of the ZEISS Ventures, which is the corporate VC of ZEISS, and SCANTINEL was funded. And then in this year, so actually we have announced a few days ago, we have closed our Series A fundraising round with the lead investor, and I will talk about this later on. But as said before, our roots belong to ZEISS. This is clear, and we also combine different areas of competencies that are quite essential to have an FMCW compact solid state product. For instance, we do have a lot of competencies in laser technology, and this is very much important, especially for FMCW. Then in photonic integration and scanning, of course, in optics with all the history of ZEISS, but you also need some competence in software and electronics. I was talking about our lead investor. It was mentioned and published a few days ago. It is Scania Growth Capital, and this is the corporate VC of Scania in the Volkswagen Group. So we are now backed by ZEISS with the ZEISS Ventures on one side, and on the other side with Scania, which is a very nice combination from our perspective, because it gives a solid technology foot and another solid application foot that is directly connected to all the autonomous mobility activities that are done within Scania, but also with the full Volkswagen Group. So what is FMCW? Let's maybe start explaining what is time of flight, because this is the most known approach to LiDAR. So time of flight, you have a system that will emit a high peak power pulse of flight, and this pulse will travel, will hit a target, and then will come back and will be then detected by the system. So by counting the time that it takes to the pulse in doing all this traveling, you can, and knowing the speed of light, you can then reconstruct the distance at which this object was interacting with the light that was emitted by the LiDAR. So this is the time of flight system. A different approach is called FMCW, is also called coherent detection. FMCW stands for frequency modulated continuous wave. And in this case, you have a continuous wave laser light that is emitted by the system, where you change the frequency. So you modulate the frequency. You don't have pulses anymore. You have a continuous wave of light, and you modulate the frequency. So again, the light will travel and comes back with the same shape. And what you do in the FMCW system and in coherent ranging, you have one local oscillator, and your local copy of the light is then mixed with the light that comes back after the interaction with the object. So by mixing those two lights, you get the so-called bit signal. And the bit signal has a very important, it has a very important information. So if you then do the FFT and you count and you take the frequency of the bit signal directly from the frequency, you can estimate the distance of the object that you have in front of you. A second very peculiar and important information you can retrieve with this coherent ranging, and by using the Doppler shift, is that you can also estimate the velocity or the relative velocity of the objects in front of the camera. So for instance, the FMCW has a very big advantage, because in every pixel, and not doing post-processing, you do estimate the relative velocity of the object that you have in front of the camera. This is very, very much important, and we are collecting this feedback anytime we speak with customers, not just for object detection, not just for object classification, but especially for object tracking, because you don't need to wait multiple frames to see how the object is moving, but you already have the information about the relative velocity of the object, and this makes all the perception activities of the vehicle way easier, and then you can also drive safely, which is the end goal of autonomous mobility. Now, if we look at the history of LiDAR, everything started with time of flight at 905 nanometer. This is because that was the available technology. There are some big drawbacks of 905 nanometer. For instance, there are quite tough eye safety limits with this line width, and this stops the range you can achieve with such type of systems to short range. On top of this, 905 nanometer time of flight systems are subject to ambient light interference as well as other LiDAR interference. Because you can imagine you have a detector and you emit a light, but then this detector is sensible to any light that comes back. So it can be sunlight, but it could also be the light that was emitted from a different LiDAR. So that's quite a big interference also with other vehicles that might be soon around in the streets. Also, time of flight is not able to measure the object velocity measurement. But of course, those are the systems with a higher technology maturity level, and they are the systems that are out in the market in these days. Then a second wave started on 1550 nanometer, and here again the first step was time of flight, and it's kind of following the same history of radar. Also, radar at the beginning started with time of flight and bulky system, and then what we know now is our system that are based on FMCW. So it's kind of following the same approach. So why 1550 nanometer? That's because at this wavelength you have less less stringent limits in terms of eye safety, or the limits you have at this wavelength permits you to emit more power, and in this way you can reach longer range. So with those system you can achieve 200 meters, and this is essential, especially if you want to target highway pilot, or if you are working on vehicles like trucks that needs to take a longer time to take a decision. So this is quite relevant, the long range. Again, being time of flight, they are also subject to interference with other LiDAR, and they cannot measure the velocity. But the biggest drawback of those type of systems is that to reach long range, they still need to emit a high peak power, more than 1 kilowatt peak power. And this is kind of a big drawback, because the photonic integration is not possible due to this reason. And peaks and photonic integration is the key enabler for cost reduction and system scale up. And I mean, if you want to scale up in volume, you have to think about a system that is highly integrated. And in this way, you can also drive the cost down, which is a key parameter in the automotive industry. So with FMCW then, and that's the third wave, you have low power continuous wave laser. And for instance, we do only need 100 milliwatt output power per channel. These systems are immune to interference from ambient light and other LiDAR, because they are doing a coherent ranging detection. As said, they can also measure direct velocity in every pixel. And most important of all, given the low power that is required per channel, you can think of photonic integration, and then you can then think of highly integrated solution that can scale up into high volume. So, which is our approach and our value proposition in this field? We have a so-called optical enhanced array in terms of scanning, and this is a quite unique approach. We do combine silicon photonics and optical collimator to have a solid state scanning approach. And this is also so not targeting to not to have moving parts is something we also hear as a feedback from our customers, because this will enhance the reliability of the system. Not only that, we do also work on the integration of the swept source, so the integration of the laser. And for FMCW, you need to have a very narrow line width below 100 kilohertz and high linearity, because you have to modulate the frequency of the laser. So maybe here is worth to mention, this is where indium phosphide is entering in the game. We do work on a silicon photonic platform that is based on silicon nitride, and then we have the laser integrated. So the laser is on indium phosphide and then is integrated on the silicon nitride platform. As said, with very narrow line width and high linearity, you can have superior signal to noise ratio, and you can reach over 300-meter range. We actually have done some studies, some feasibility study for system that looks at 1 kilometer for the train applications, for example. So this is really where the FMCW is a game changer. Long range and highly integrated solutions. So silicon photonics is also a very nice technology from our point of view, because it enables also the parallelization of multiple FMCW channels. And this is essential to achieve high mega points per second data rate. And of course, all those systems are targeting the maximum amount of mega points per second, also based on the refresh rate. But you can do this only if you parallelize multiple channels. What we get out of this is a 5D point cloud, meaning that we measure X, Y, Z, so the distance, the 3D distance, but we also measure the velocity and the reflectivity. And those two additional information, as said, are quite relevant for detecting the objects, to classify the objects and then to track them. And as said, silicon photonics, and we are quite stringent on this. We only select technologies that are CMOS compatible, so that then the manufacturing can be done in high volume, achieving a highly competitive price position, which is really, really important, as said, in the automotive space. Where are we now on this roadmap in terms of peaks? The peak is out of the fab. We have announced it in February. We are already doing some tests on this, and this system has already 256 lines in the vertical field of view. So the scanning is already done with quite nice resolution. With this one, we will be able to build our A sample by the end of the year. How does the market look like? Well, just if you look at market studies, it's a exploding market in the upcoming years. Of course, there are still some questions in terms of acceptance, but it's the news. I mean, in Germany, I think the news was from 1 week ago. That also here it seems possible that now autonomous vehicle can drive on public roads. At least the discussion is there. And we are talking with customers in China and in the US. They are saying they are already having robo-taxis out in the streets, and they foresee they could charge some price there. They can get some revenues in 2 years, 1 to 2 years, especially in China. In terms of segments, there's quite a lot of movement in the private vehicle, even if it's not fully clear when it will be out in the streets. But the first use cases we are seeing here are the highway pilot, where the vehicle will autonomously drive in highways. And for this one, you need long range, of course, because the speed is higher, and then high resolution because you want to detect very small objects in front of you, and you want to know if they are objects that are moving, or how to handle those objects in front of the car. Then there's a very nice segment is the delivery vehicles. Here we can combine, there are two different aspects, but one is on robo trucks to move goods from point A to point B in an autonomous way. And here the business case is quite strong, because if you have an autonomous vehicle, you can get rid of the driver, or you can have the driver driving for more hours, because then most of the time it will just sit there and check that everything is fine. And this is quite a strong business model. There are also some laws in the US where you create some corridor for robo trucks, where they are moving autonomously from one city to the next one. So this is an expanding one. Mobility service, here we have robo taxis and robo shuttles. Two scenarios. One can be robotaxi in the city, and as said, we have customers that are already deploying their fleets in the streets of cities in China and the US. Whereas robo shuttles can be thought like the shuttles that moves off public roads, like in airports, or in harbor, like those places that are not public roads. And then we have the industrial segment. This is also quite nice, because it's of course off public roads, like mining, agriculture, and also logistic. So this is maybe a smaller market, but still interesting. Then let me share some results we've got in the last months with our demonstrator. So here we were able to measure with high resolution up to 120 meters. And here you can recognize in the scene those buildings, this house, this bar, those trees. And the same applies here below. That's a different scene, but you see the car. And you can even see within the car, you can even think you can check if there's a driver or not. So you can see if the vehicle is moving autonomously or someone is driving it, because you can see through the car up to the seats. Of course, those are trees, and here you have another building, and so on. So those are real data we were able to capture in the last months with the demonstrator we have. We've also done some snow measurements and heavy rain measurements, and maybe this is worth an additional mentioning about FMCW. What you do with FMCW is more close to a tomography. So along the line, along the scanning line, you could see multiple peaks. And this is a big difference between FMCW and time of flight. Time of flight does react on the first thing that comes back, and then you just know that something something hit the target. So the light hit something and then it came back. With FMCW, you do a different thing. You do the tomography along all the line, so you could have multiple peaks. And here you see, this is, for instance, one case where you have two strong targets, 7% reflectivity and 40% reflectivity, and in front you have strong rain. So here when you then do the analysis, you will see multiple peaks. The highest peak will be, of course, the high reflectivity target, but you can also detect additional peaks due to the raindrops that you are intercepting along the line. And when we were discussing this with customers, they also said, yeah, this is quite important also when you think about dust, or when you, for instance, in China, there are a lot of building spots where you have a lot of dust. So it's important to know that there is dust, but that there is something else behind the dust. So this is also a very important feature of FMCW. Now going to a summary, and then we can go to questions. What I've shown today is that FMCW is expected to be the end game of LiDAR. And this is not my sentence, but is a quote of one of the investors we were talking to in the last months. We are working on solid state FMCW LiDAR, and we are exploiting integrated lasers, highly parallelized and solid state multi-beam scanning. And we do see that photonic integrated chips are the key enablers for system integration and cost optimization. Now, if you have any questions, I will be happy to answer.
Yeah, thank you very much for this interesting talk. And yes, as Davide already said, if you have questions, you have in the navigation bar, you have this button reactions, and there you can raise your hands. There's a button, raise hands, or you can type the questions into the chat, and then I will read them out. So first questions. Oh, okay, Victor, do you have a question?
Yes. Hi, thank you, Davide, for the nice presentation. You mentioned that there are already some demonstrations you have done with FMCW. I believe you mentioned 115 meters or something like that. So I was wondering, could you comment on what are the bottlenecks at the moment for you to increase that distance or to improve the resolution? Are where are the technology bottlenecks? I'm thinking maybe you want to achieve a laser with a lower line width, or the interfaces between the 3.5 and the silicon photonics should improve to have lower losses and have a little bit higher power in the far field. What are these technical limitations at the moment?
Yeah, I think you've mentioned the most important ones. So with the A sample, we target to measure 200 meters, 300 meters range, and this is because we are changing the lasers. So we're getting a better line width, and also higher power. So it's a combination of the two. So the laser source is very important in this case. You have a narrow line width, and then the power of the laser itself, it's important. Of course, then being processed by silicon photonics, all the losses are very relevant as well. So in the next step, we have to work on the efficiency in terms of losses, but also if you think about not just about the range, but if you take a holistic view of the system, the power consumption is also playing a big role. So then making a more efficient switches, for instance, in silicon nitride, this is also something we are working on, because at the end of the day, the power itself, it's a very important feature of the system.
Okay, thank you.
Okay, then I have a question from Peter Harmsma. You mentioned 256 channel device, but the point cloud in the picture seems to have more pixels than that. Can you comment on the scanning mechanism?
Yeah, so what we have done now is what we call the demonstrator. There we have a system with just 12 lasers. And then to enhance the resolution in standstill scene, we did apply a goniometer. In this case, we were able to make a finer resolution. What we will have as a next step is these 256 lines in Q3 this year. But then the idea is that you have a modular solution. So if you want to enhance the resolution in the vertical field of view, you can have multiple modules so that you can have more lines. Maybe worth to mention here, we have 256 lines and we parallelize 16 channels of FMCW. So we have 256 lines and 16 channels in parallel.
Okay, but if you say you would combine two devices, is really the resolution getting higher because you have to put them in line, that they work together? Is this possible?
Yes,
Because
you can synchronize them.
Synchronize, yeah, that's what I meant. Okay, okay.
Yeah.
Great, okay. Further questions?
I am unable to digitally raise my hand.
So
okay.
go ahead.
Okay. I have three quick questions. First, I would like to know more about the lasers you're using. What sort of laser is that, and how do you modulate so nicely the carrier frequency?
It's an indium phosphide laser DFB at 1550. This is what we are using now.
All right.
And if you want to know additional details, I'm probably not the right one to give you all the technical details on laser modulation. So we might have a chat with our experts.
Okay, yeah, that would be really interesting for me to learn more about that.
But the line width, so we have the coherence of the laser is below 100 kilohertz, and this is very important for a system because then you have to modulate it and you have to reach these 200 and plus meters. So that's why it's very essential, and also linearity, because as you see we are modulating it. So those are the two very important features of the laser, as well as power. Yeah.
Concerning that detecting technique, are you applying some sort of filter, like a spectral filter or polarization filters? Does that help to enhance the signal to noise ratio?
We are considering them. In the A sample, we will, maybe I'm confusing here, but of course, I mean, this is a topic under discussion. If not directly in the A sample, will be for sure in the B sample. So this is actually really helping the signal to noise ratio enhancement. Yeah.
Thank you. And finally, I wanted to ask if laser speckle is also limiting your resolution.
What do you mean?
I mean, this whenever you illuminate a grainy surface, you are experiencing.
Ah, the speckle. Yes.
Like a
Yeah.
little speckle, right?
Yes, on one side is yes, on the other side is also no. I just heard about this discussion. It also helps you to somehow smooth some errors, but also here I don't know all the details. So for sure, speckle on one side it doesn't help you. On the other side is kind of smoothing some errors you might have.
Yes, as objects are all in motion, so this could
exactly
a little bit, depending on the time resolution, you may have
exactly
static, more or less static interference situation, which could cause trouble. So maybe for those two detailed questions, I would be happy to talk to your colleagues.
Yeah, if you reach out to me, then I can forward the request to our technical.
Thank you very much.
Yeah.
Okay, thank you. Further questions in the chat? No. So if you have a question, you can activate your microphone, I would say. If not, I would suggest that we come to the last point of our today's meeting. Again, David, thank you very much for this interesting talk. And now I would hand over to Professor Jürgen van Erps from the Vrije Universiteit Brussels, so that he can give us some insights about the Innovation Support Fund, which was already mentioned. So, can you share your screen? Perfect. Yeah.
Let's try to go to full screen as well.
Yes, perfect. Yeah,
okay,
it works.
Okay.
Thank you.
Thanks a lot, Hendrik, for the introduction. So indeed, in this final part, I just want to mention a few words about the practicalities of the Innovation Support Fund that we have set up. So basically, there is currently a call for applications that is open for small and medium-sized enterprises that are located within the Northwest Europe region as defined by Interreg. And the target users are actually SMEs that are ready to scale up the production from a trial series beyond the proof of concept demonstration. And we have an amount of 7 vouchers available, which are each worth up to 50k euros. And the technical support that is being provided under the voucher scheme is, of course, access to the OIP4NWE pilot line, which covers your PIC design verification, manufacturing of the PIC, also including potentially external optics and packaging of the devices. And so the call, as mentioned, is currently open and is open until the end of September. So 30th of September, the call will close. And we expect to be able to announce the winners 1 or 2 months after call closure. All the detailed information can also be found on the link on the bottom there, so OIP4NWE.EU/vouchers. And yes, what I didn't mention is that there is a 20% financial contribution expected from the SME up to the maximum of 50k support. And then, of course, if the total project budget goes beyond that, then of course anything above that should be funded fully by the company. All right, so in terms of requirements, I already mentioned that the company should be a small or medium-sized enterprise and should be based in the Northwest Europe region. So it's basically UK, Ireland, Belgium, Luxembourg, part of the Netherlands, part of France, part of Germany. So you can have a look at the area also on the link provided here. And the idea is also that the company should have a PIC design ready. So it should be already at a TRL stage 4. and aimed at scaling up the production. So let's say that's real proof of concept type demonstrators where a company would not have a design ready is at this stage not eligible for the vouchers. Then the applicant should demonstrate a kind of business case to prove some impact in their future business of the outcome of the technical realizations that would be done under the voucher scheme. Of course, compliance with state aid rules should be overlooked. And I will also briefly introduce in the coming slides the voucher application form that needs to be filled out. And finally, since we are trying to also further promote the activities of the pilot line, and the voucher recipients should also agree to partially document their use case for further dissemination at a later point in time. So the application procedure itself basically can be looked at as a two-step thing. The first one is optional. So we have an expression of interest form that can be found on the website that was mentioned earlier, which is basically a one-pager with some information, contact information, and really a brief description of what you propose to do, so that we can do an early eligibility check, and as such avoid that if you would not fulfill all the requirements, for example, that you avoid having to do all the work in filling out the entire application form, but that we can do the eligibility check at an early stage. And if that is all positive, then there is the full application form to be filled out and submitted before the call closure. And the application form consists of the following parts. So in the beginning, there's just some company information, contact details, and so on. You will also see that some fields are marked with an asterisk, and this is basically the indication that this is information that would be be made publicly available. So it's just like a short abstract and a couple of informations about the target field and so on. A general description of the technical specification and technical works to be done, and in part B you have the business side of things. So there's a brief description of the business case and target markets, validation, route to market, unique selling points, and a short business plan, with the ultimate aim at looking at impact of the technical support. So either new business being generated as new revenues, or additional employment within the company. So this will allow us to do then the evaluation of the submitted proposals, and we will do the evaluation according to the following criteria. So we have basically 4 items that we will look at. The first one is the innovative character of the project. Just looking at the technical aspect of things. The second point is also technical feasibility and the quality of the project plan. And then the third item that we will look at is credibility and level of commitment of the company. So that's also partly why we expect a small financial contribution from the applicants. And finally, the added value on the business case and potential impact of the project. So each of these 4 items has a specific weight, and the individual score on each of these criteria should be at least 2.5 out of 5, and then the total score should be at least 20 out of 30 to be eligible for the vouchers. If multiple vouchers or let's say multiple applications are being received, and then the selection committee will also try to target the geographical distribution within the Northwest Europe region, as well as potentially distribution over different application sectors. But these are just additional criteria that would be taken into account if you would have a massive amount of applications. So that's basically the short explanation on the voucher scheme. So if you have any, if you need any further information, there is a detailed description on the website, so OIP4NWE.EU/vouchers. And there's also this email address, voucher@OIP4NWE.EU, which can be contacted at any point in time if you have any questions or any further comments about the voucher scheme. Thank you very much for your attention. And
yeah. Thank you, Jürgen, for your talk. And do you have already first question right now on the vouchers or on the pilot line again? Or to Davide Canavesi? Seems that we have no questions, so I think your talk was very complete.
okay, thanks.
So, but again, if there are further questions in future, you know how to find us, to find the project, the email addresses, and so on. I would suggest that I would connect or share the email addresses from Georg Bastian to Davide, so that you can get into contact about these further questions. And then I would like to say thank you all for attending our webinar. We hope that you get some inspirations, and hopefully you will can join our pilot line, test our pilot line due to the vouchers. And yes, thank you very much, and see you soon.
Very much. Thanks. Bye bye.
Thank you.
Bye
Bye
bye.
bye.
Thank you.